Hi, my name is Travis English with Kaiser Permanente, and this is our HVAC Design Excellence HVAC Design presentation about being brilliant at the basics. We're going to go through the top five design issues that we come across when we're looking at HVAC designs and talk a little bit about our design expectations for excellent HVAC designs. Um, so in terms of quality and what we're looking for, we're always looking for our engineered systems to be affordable. We want to be cost sensitive. Affordability is part of our primary mission in healthcare. And then we want our systems obviously to work and to work well or flawlessly. And then we have a focus on energy. We obviously have energy goals as an organization, very aggressive energy goals as an organization. And so we need to be cognizant of that while we're designing. So through these next couple slides, I'm going to walk through the top five list of design issues that we're dealing with in the portfolio now. This is August of 2019, by the way. And so it may be outdated by the time you watch it. But those top five issues are load calculations, 8760 calculations, acceptance criteria, controls design, and then ventilation calculations. We'll spend a significant amount of time on ventilation calculations. It is not accidental or coincidental that 3 out of the 5 have the word calculations in the model. Most of what we have issues with have to do with design engineers and really the robustness of the calculations that go behind the design, which tends to be what we check. So first off is load calculations. We absolutely check consultants' load calculations, and we very much have expectations around where those calculations should land. For our medical office buildings, outpatient clinic buildings, we're looking at 300 to 500 square foot per ton. The newest wave of medical office buildings that we're doing are over 500 square foot a ton. For the hospitals, 250 to 400 square foot a ton. A lot of the legacy buildings, we still see systems that come in with more tonnage than that. But we want to have a conversation around that every time. And then we have some checksums for heating as well, 5 to 10 or 10 to 20 BTU per square foot for those systems. And the reason that we want to review your load calcs and have a look at them relative to the checksums is that if you are struggling with a calculation issue where your load calcs are coming up with larger systems or smaller systems, then we can help you validate the assumptions. We have a pretty good list of assumptions for most of the spaces in our buildings. The second piece of calculation math that we ask for is these 8760 calculations. The sort of line that I like to give on this is that as design engineers, we're very good at designing for the peak hour of the summer. And we're also typically pretty good at designing for the peak hour of the winter or the coldest hour of winter. But unfortunately, that's only 2 hours a year, and that leaves 8,758 hours that we really don't have a good design for. And that doesn't work with a lot of the systems that we're putting out in place, particularly central cooling systems, chillers, pumping systems, boilers, and boiler pumping systems. If you've never done an 8760 calculation and an 8760 hour load assessment, I like to say it is a life-changing experience. The one on the right there you can kind of see is a boiler load profile for one of our buildings. This building was on the east coast of the country. The design engineer had originally put in a system where they had 2 boilers, and I think each one of the boilers was about 10 BTU per square foot for the building. But when you actually looked at the load calcs, the maximum hourly load we were able to find throughout the year was more like 5 BTU per square foot, which would be 1 boiler running at 10%. And then as you go down the bell curve, 80% of the annual hours, the boiler load was extremely small, like less than 0.05 BTU per square foot, which basically means that you would have a boiler system that needs, something like 100 to 1 turn down, or which obviously boiler systems don't have. And so you have to think about volume, you have to think about pumping, you have to think about minimum GPMs, you have to think about a whole bunch of different things. And that is normal for our systems. that we do need to go through that thinking because we want these systems to operate effectively and efficiently most of the time and all of the year. And so we definitely demand that of our design engineers, many of whom haven't done it before, and it's kind of the first time. So, and that brings us to acceptance criteria. Acceptance criteria is something that we started requiring out of our designs, I think about a year and a half, maybe 2 years ago. And that is that what we found is that commissioning agents are very good at validating system performance. They will go out there and measure temperatures. They will go out there and measure fan KWs. They will go out there and measure all these different parameters. However, if we don't tell them what they need to measure to, then the commissioning process is significantly less effective. And so we've started requiring the design engineers to actually state numeric criteria that are the conditions of acceptance. And I like to think of these as two buckets. The first bucket of acceptance criteria are the criteria that mean the systems are in control. All the set points in the building need to be plus or minus 3, or all the temperatures in the building needs to be plus or minus 3 of the set point. That means that the temperatures in the building are in control. Supply air temperatures and supply water temperatures need to be within plus or minus 2 of their set point. That means that those temperatures and those water systems are within control. There's also pressures, water pressures or supply air pressures. Those need to be plus or minus a reasonable latitude of their set point in order to be considered in control. So that's the first bucket of acceptance criteria. We need to define numerically what it means for our systems to be in control. And sometimes our commissioning teams like to think about this in 2 steps, right? First, get the systems in control. Now, the system's in control, you could be looking at a building that is an energy dog and none of the energy features are working, but at least the systems are in control and we can make that as a positive statement. The next set of acceptance criteria, again, that need to be numeric, have to do with energy functionality. When we design economizers, we need to state what the predicted position of the economizer is for every condition of outside air, and then we need to go measure it and make sure that that economizer damper actually is where it is supposed to be. And on cooling plants or rooftop package units, we do have a predicted KW that we should see during each load condition. We can go out and measure and make sure that that's happening. With the heating plant, we go out and measure that the actual consumption of the heating plant is what we predicted it was going to be. So that's that's the second bucket, right? Energy functionality. And all of these need to be numeric. And acceptance criteria that doesn't have a number in it becomes an unenforceable acceptance criteria at the end of the project. So that's acceptance criteria, which brings us kind of to the long part of the discussion that we're going to have that has to do with ventilation calculations. The ventilation calculations in healthcare buildings are really kind of the keystone of the whole system design performance. So to get the easiest stuff out of the way, when we do our medical office buildings or outpatient clinical buildings, we do not follow ASHRAE Standard 170 or California Table 4A. Basically, we don't use those standards unless it's required by law, which means that in most of our outpatient clinics and medical office buildings and even D&T portions of inpatient clinics, we use Standard 62. I think every consulting engineering firm has some form of calculation methodology for Standard 62. Trace actually includes the calculation for Standard 62, so you can go ahead and use that. The more complicated and what we're going to talk about a lot more systems are the hospital systems, where you do have to use an air change table, either ASHRAE 170 or the California Table 4A, and look up air changes for the various spaces within the building. So we'll talk a lot about that. Again, we do have some design expectations. We don't like to see that supply air total or the supply air maximum higher than 1.2 CFM per square foot. That really is the top end of what we expect to see on kind of the non-OR systems. And then outside air, a little bit of conversation around outside air. We don't expect to see a hospital require anything more than 0.2 to 0.3 CFM per square foot of outside air. That tends to also line up with where the overall exhaust systems are going to be. And so sometimes we have design engineers that, wind up with 30 or 40 or 50% outside air systems because of the way they're doing their calculations. And that's generally not, we don't want to see that. That should not be correct. The reason that ventilation system design is so important in hospitals is because the single largest consumer of energy in hospitals is reheat energy. That's where we use more energy than anything else. And the reheat energy in a system on an annual basis is a function of the minimum air of the system. So I call this the neutral condition, right? Whatever the CFM is of the system at the neutral condition defines the annual system energy. So just to talk about neutral condition, I live in California, and so in Southern California here in Long Beach, when it's April and it's 3 o'clock in the morning on April 1st, and the outside air temperature is 69 degrees, right? Which means there's no heating load, there's no cooling load, there's very few people in the building. Any lighting system that can be off is off. Any equipment that can be off is off. Any patient that can be asleep is probably asleep, and we're down to a skeleton crew on the night shift. That's the neutral condition for a hospital. The amount of air that we're using at that condition is the minimum air of the system, and that drives the energy signature for the hospital. And so in order to meet our energy goal for hospitals in general is 125 EUI points. So if you assume that roughly 10 EUI points of that is lights and another 10 EUI points of that is plug loads, then we want to get right around 100 EUI of our HVAC systems. In order to get there, you've got to be somewhere in the neighborhood of 0.3, 0.4, maybe maximum 0.45 CFM per square foot at the neutral condition. Right. So, and we do, by the way, assume that our systems, if you have economizers and resets, obviously that puts you on a lower curve than if you don't have economizers and resets. So generally, we do require both economizers and resets as part of our designs. So let's just start talking about system design and the actual spaces that are in the system. This is a little database that I've been putting together as we review air handling systems. So out of 750,000 square feet, what are the top 10 types of spaces that you'll find in the hospitals? And the answer is number 10 is patient rooms, 15,000 square foot of patient rooms out of 750,000 square feet. It's important to note the other metric that I track is that I look at our design engineers supply air that they generally design at the peak. And so we see design engineers designing at an average of about 9 air changes per patient room, right? So there's a lot of opportunity for turn down in that. Number 9 is exam treatment rooms, 16,000 square feet out of 750,000 square feet. And we're seeing engineers designing those for about 8 air changes, 7.8 air changes. Again, lots of opportunity for turn down. Number 7, conference and multi-purpose rooms. These are not even covered in Standard 170 or Table 4A, but they're fairly frequent within the projects that we do. And we see them designed for a peak of 8 air changes per hour. Obviously, those rooms spend time where they can turn all the way down. You can actually shut them off if you want. Equipment rooms, electrical rooms, those are fairly frequent within our hospitals, believe it or not. And that includes equipment rooms for imaging equipment rooms that are associated with clinical treatments. And so we tend to see a lot of air into those spaces. Sometimes it's smart to separate those off onto separate systems so they don't mess up, kind of the strategy for the air systems. What are we on? Number 5, 10, 9, 8, 7, 6. Oh, this is number 6. Number 6 are the clean workrooms and storage areas. These square footages, by the way, at the top of 10 through 5 are not terribly far separated. We see engineers designing those a little bit higher than code minimum. Now we're into the top 5. The number 5 space is toilets. in restrooms and showers. We have lots of private restrooms in hospitals, and generally we do not see supply air going into those. They tend to be exhaust only spaces. We do have some engineers that put supply air in there. That's why you see an average of 2.2 air changes of supply air. But they don't really need supply air. Those are neutral load conditions, and you can drag transfer air from a nearby space and just do exhaust. Storage rooms, we have a lot of storage rooms in hospitals for all kinds of different purposes. We'll talk a little bit more about space designation later, but most of these probably don't need specific air change rates, or to use ASHRAE 170. Most of these are really just storage rooms. Patient rooms, oh yeah, the number 10 one was patient rooms for ICUs. So the number 3 one is actual patient rooms, normal med-surg patient rooms. And again, the design air changes that we see engineers giving about 9.3, about 9.1, which is a summer condition, right? That's for 3 p.m. on the summertime. In the neutral condition, anywhere else in the country, you can drop that down to 4 air changes. In California, you'll likely be in economizer mode using 100% outside air, and you can drop that down to 2 air changes. Number 2 space is office. This surprises a lot of people, but really about 20% of our hospitals is not even clinical, right? Patients never go there. Up to 25% can be areas that patients never go to. So it's office space, it's admin space, it's workroom that is not clean workroom or soiled workroom. It's just working areas where our docs and nurses and our staff go about their business. Most of the people in the hospital are staff. And then, of course, the single most common space that occurs in hospitals are corridors. We have, I think the statistic is that we have like a 1/4 mile of corridors for every 100,000 square feet. And hospitals are notorious for having these like super long corridors that you're always walking down. And we use a ton of air in those corridors, which really can drive our energy signatures. Our average design engineer puts 5 air changes into those corridors. The code now in California and nationally is starting to line up around 2 air changes, and even that is completely unnecessary. In terms of cooling load or air quality, you really don't need to do anything more than fart air through the corridors. And so there's really a lot of energy that gets wrapped up in corridors. So that kind of gives you the feeling here when I talk about that we need to have air systems that turn down in a neutral condition. We have a peak supply air of maybe 1.2 CFM per square foot across the system. And in order for energy conservation, we want to get that 3 a.m. neutral condition down to 0.3 or 0.4 or 0.5 CFM per square foot. There's plenty of opportunity to do that between the peaks that we're designing in these spaces and the turn down condition that we can have in these spaces. So just to talk more in detail about the neutral condition, when I talk about the neutral condition that we need to design for, because what we're now requiring our design engineers to do is to specifically design for a neutral condition. The peak condition obviously is when the temperature is the highest in the summertime or when the temperature is the lowest in the wintertime. You can see those. But a neutral condition is the condition when your outside air is between 65 degrees and 75 degrees. So basically no cooling load, basically no heating load. Obviously in the neutral condition, you want your relative humidity to be neutral as well. In some climates that just doesn't happen. And also, I think the neutral condition should be designed overnight, where it's between 11 p.m. and 5 a.m. So the sun is down, there's no solar load, and you're generally dealing with the night shift, and any patients that are essentially living in the building, most of them will be asleep during those hours. So during those hours, that truly is a neutral condition. And you can kind of see this is a pretty broad spread of climates, right? From Atlanta, Georgia to Houston and Phoenix and Seattle, and then Los Angeles and Sacramento. In each case, there always is a neutral condition that you can design for. And so that neutral condition and the specific design that we do for the neutral condition really drives the annual energy performance because it sets up our system responsiveness. So one of the exercises that you have to do, and this was an engineer that did it particularly well, is to go through the building and actually look at where can we turn down systems and how far can we turn down systems within the neutral condition. There are going to be some areas where you can essentially turn down systems to, very low load or shut them off entirely. And in this map, those are the green areas of the building. And then there are areas where you can turn down systems, but you probably need to, either for pressurization or for code reasons, you probably need to maintain 20, 25% of air in there. And then there are other areas that you just can't turn down that legitimately need to run overnight and legitimately need to run 24/7. But it's good, it's great to put these things on a map because you can kind of see there's a lot of green areas here and there's a lot of yellow areas here. So the amount of area that's red, obviously what we would try to do there is minimize the amount of air that we're putting in there all the time. But for these green and yellow areas, we would maximize the opportunity that we have between the hottest hour of the year when we need the most air and that neutral condition when we really shouldn't need much at all, if any. So for Californians, this obviously is a paradigm shift because for many, many years we've kind of had this idea that OSHPD doesn't allow VAV systems. And the way the code actually works is that OSHPD requires the California code only. It's unique to California. Out of the 50 states, there are 49 that don't require this and one that does require this. But California requires return air VAV boxes for every supplier VAV box. I should say return air or exhaust air VAV boxes for every supplier VAV box. That's been in the code since the 90s. And so we've been working with OSHPD on that for the last, 5 years or so. And so at this point, we do have 7 or 8 precedent projects where we've submitted alternate methods of compliance, going back as far as 2016, where we do not include the return air VAV boxes. And there's a rational basis for it, right? We're in spaces where there's no pressure requirement, then we're not doing return air VAV boxes. And so these AMCs, if you're doing work for Kaiser, obviously will share all the previous ones with you, and so you can see the rational basis for it. But so that may lead you to believe, okay, great, we can do a variant. We don't need to do return air controls at all. Fantastic. Well, that's not necessarily true. And there is a lot of homework that's necessary here to design these systems correctly. But I'll just walk you through the logic just so that you know, right? So for negative pressure spaces, generally you're not going to need any return air controls because in general we're putting those on a constant volume exhaust air system. The exception there are 100% output air systems where sometimes we would have a VAV exhaust that goes along with our VAV supply. For positive pressure rooms, there's 2 ways to go about that. You can do some return air controls and make sure that they're tailored to your supplier controls, or you can just make that room constant volume. And in making it constant volume, the smart thing to do sometimes is just to plug it into the exhaust so that you always have a constant volume exhaust coming out of that. Obviously, for larger spaces like operating rooms or procedure rooms, you might not want to do that. The return air controls is the better option. But for small spaces, those low positive pressure spaces like clean work rooms or med prep rooms, then often the easier way to go about this is just to plug that onto a constant volume system and provide it with positive pressure all the time. That brings us to the no requirement rooms. The no requirement rooms is where we have to start looking at the room in relationship to the zone, in relationship to the system. Every room has a room turn down, and that is the turn down that goes from the supplier maximum to the neutral condition minimum, right? But every room is associated to a zone. Some rooms are on their own zone. There might be 5 rooms on other zones, right? So you look at all the rooms together and sort of the minimum turn down between the maximum and the minimum condition gets applied to the zone. So then you have a zone turn down for each zone in the building. The system turn down is the sum of all the zone turn downs. So you take the rooms, then you go up to the level of looking at the zones, you figure out what the turn down is available at the zones, add all that up, and that becomes the system turn down. Then you have to go back and look at the return air. If the system turn down is significantly more than the zone turn down, that means that that zone could go positive. So overnight, let's say you have a zone, during the day it's 100%, and at night your supply air in the zone can turn down to 50%, but the supply air in the system can turn down 70%. Well, that zone could go positive. And so return air controls will not help in that scenario. What you need to do is look at the system turn down relative to those zone turn downs. On the other hand, if your system turn down is significantly less than your zone turn down, then that zone could go negative, right? And that is where return air controls can help. And so that could be what we've been seeing with the design engineers. That could be in quadrants of the building, right? Where the zones are turning down, to a radical degree. Like let's say you can shut down all the green zones in that one quadrant over there. So your zone turn down basically goes to 10%, but your system is only turning down to 30%. Well, in that case, a single return air control, at a main duct that just shuts down return air to that quadrant of the building or severely limits return air to that quadrant of the building could be the right means. Now, these deltas, you'll see that I'm using this sort of double greater than or double less than sign, because these deltas do need to be reasonably significant. Anything less than 100, 150 CFM per door, a lot of doors get left open, and a lot of doors that are closed are not, sealed doors where they still have some leakage. And return air does take the path of least resistance. So unless you're building up a significant pressure, significant difference, more than 150 CFM per door, then those controls might not be applicable or might not be apropos. So that sounds like a whole lot of calculation work, and it is. Which is why we're doing this presentation and talking to different design engineers. So the best thing to do is to look at an example. This is an example of a 37,000 square foot patient floor, 77 zones on the floor. The design air peak was 1.2 CFM per foot, and the peak supply air during the summer, we would be using a supply air temperature of 55 degrees. When you add up the outside air to the rooms, there's two ways to calculate outside air. The first way to calculate outside air is simply to add up all the outside air that's required to the rooms. That gives you about 0.18 CFM per square foot of outside air required. However, I still think that we need to use the standard 62 methodology because a lot of spaces on the systems are standard 62 spaces. So when you plug it into the multiple zone standard 62 calculation and make the corrections for ventilation effectiveness both at the room and at the system, that goes up. And it goes up to about 0.2, 0.25 CFM per square foot. In this case, 0.23 CFM per square foot. Now you could play around with that calculation and probably drag it down a little closer to the 0.18, but in this case, that's probably not apropos because your exhaust air CFM is coming in right at 0.23 CFM per square foot anyway. And so having 8,500 CFM of outside air and 8,300 CFM of return air is going to tend to balance. So that's the design for the peak condition. That's the design for the summer peak condition. That's the design I think that we're all used to and that everybody's done. So which means that's where the fun begins. So then what you do is you calculate the neutral condition, and you go room by room through the neutral condition and calculate, okay, what is the actual code minimum supply air that I need in the neutral condition? And that turns out to be 0.38 CFM per square foot. However, each of those rooms lives in a zone. And when you take account of the zones and apply kind of the maximum, minimum turn down on a per zone basis, you wind up a little bit higher than that, 18,000 CFM, which is close to 0.5 CFM per square foot. The next thing that you do at the neutral condition is you calculate, and I mean calculate, the supply air temperature that you'll have as a turn down, a supply air setback. And in this case, we're able to calculate a supply air temperature setback of 67 degrees, which is good. It should be higher than 65 degrees. But in order to get there, you have to look out for those zones that have 24-hour loads. In this case, in this system, there are med prep rooms which have refrigerators in them. Those refrigerators produce heat 24/7. And so what you actually need to do is provide more air in the med prep rooms so that they can stay cool at 67 degrees and allow the whole rest of the system to turn down to 67 degrees. And that air is accommodated within these air volumes. But anyway, you're looking at a supply air system turn down of 60%. The exhaust air is constant volume, which means that your return air turns down quite a bit more to 73%. And that's when you need to look at balancing around the floor and see where that return air is going, where that return air is coming from, and whether or not there is any need for return air controls. In this particular system, there wasn't. There wasn't any zone that was, significantly, that was, 150 CFM per door or anything more than that. Now, you don't have to stop there. There is even further that you can go with this, and that is each of these rooms also has an unoccupied supply air minimum, and so the office spaces on the zone and even the patient rooms on the floor can turn down in an unoccupied condition if there's occupancy sensors associated with that. The sum of the unoccupied minimum supply air is very, very small, like less than 0.1 CFM per square foot. And that's not unusual to see that way down under 0.2 CFM per square foot. However, at that point, I kind of always think that you should stop at around 30% turn down or 70% turn down. Just because in our experience in medical office buildings and office buildings, trying to get a system to ramp down from 100% to 30% is difficult enough. You'll run into challenges with coil velocities and fan capacities. VFDs can't really turn down more than 30%. And so trying to run down below 30% is really just difficult to do. So if you get down to 30%, consider it a win and move on from there. So in this case, if you were going to do unoccupied dropouts at the zones, you would probably actually want to set those supply air minimums higher than the code would allow you to do, so that you don't overdrop in the system. So that's a lot to think about, but there's more. The other thing that we've been looking at with design engineers and with a couple of design engineers is how important space assignment is. And there's 2 slides here that talk through those space assignments and really just kind of how important it is to identify those relative to that maximum condition, that minimum condition, and the available turn down. And the first one is corridors. We had in California for a long time a code that said 4 air changes total air and 2 air changes outside air in corridors. That has gone away, so now we're back down to 2 air changes in corridors. But that really is for patient corridors. There's also some other classifications to the code for resident unit corridors that still have the 4 air changes. Semi-restricted corridors, if you use that designation, then you're going to wind up with higher minimums in those corridors. Semi-restricted corridors, by the way, is a pretty defined area, and if you're not within about 20 feet of an operating room and you're using the designation semi-restricted corridor, you're probably incorrect. But the more interesting part is that not all corridors, I would say, are patient corridors, right? You could argue that a patient corridor is a corridor that's within a reasonable distance of a patient room or within a reasonable distance of an exam room, between a waiting room and an exam room, maybe, that those are patient corridors. Well, there's a lot of corridors in hospitals that are not that. That are circulatory around the admin areas or circulatory around the reception areas. Those are not necessarily patient corridors. And if you start to classify those under standard 62 rather than standard 170, that has a significant difference on your system minimums and what you can do with the systems. The same is true with work areas. And this is actually, you remember back in the chart, 25% of our hospitals are actually staff areas and work areas. There are only 2 types of work areas that are regulated by standard 170 or by table 4A, and those are the bona fide clean work areas where you're legitimately working with sterile products. And then soiled workrooms or soiled utility work areas where you're working with soiled products, and those require negative pressure and exhaust. The clean ones require positive pressure and 4 air changes. But honestly, if you go through a hospital and sort of audit those spaces, there's not that many of those at all. We have a whole bunch of rooms for work areas that are not clean and they're not soiled, right? They're just work areas where our staff works. We call them chart rooms and reading rooms and control rooms and workstations and work areas and copy rooms. There's all kinds of names for those things. And those are effectively just office space. That's the area where our staff works, and there's not really any patients associated with that. So if we can classify that stuff under Standard 62, then obviously that significantly changes the system requirements. Storage rooms is another area like that. We do have certain rooms that are regulated that require certain air changes under storage. And there's like blood bank tissue storage or clean linen storage. I still don't know why that is a thing. But then hazardous material storage, anesthetic gases. So we do have these specific storage areas that have requirements. However, most of the storage areas in a hospital are not those, right? Most of our storage areas, again, are associated to our staff areas. And so we have just your standard issue storage closets for staff and for materials. And those are not regulated storage areas. And so if you start to look at that, and parse those spaces a little more discreetly, there's a big the biggest one, actually, in terms of magnitude, are waiting areas. ASHRAE 170 and Table 4A regulate waiting areas where there is an opportunity for a high risk, undiagnosed tuberculosis or chickenpox patient to come walking in, with an airborne disease. And so they require 12 air changes per hour and 100% exhaust, which is a ton of air, right? And so where you have those, and they're very specific about it, there's the ER waiting room and the radiology waiting rooms. And then in California, we extend that to the nuclear medicine place, and we actually have a designation for primary care waiting rooms, which don't exist in hospitals. So those are the areas that there's a legitimate concern, and we are treating that with exhaust air, 100% exhaust air, and a lot of it. But again, most of the waiting areas that we have in hospitals, pharmacy waiting, clinic waiting, just the general seating that we have around the lobby of the building, those are not ER waiting rooms or radiology waiting rooms where we're very worried about tuberculosis risk. Every patient floor has a couple of family waiting areas where the families can hang out. Those are also not 12 air change per hour, 100% exhaust waiting rooms. And so if we start to parse those up more carefully, it has a significant difference on exhaust air and outside air. And then restrooms. Restrooms is a weird area. There's been some conversations in ASHRAE 170 where they say that, look, the restrooms that we have, this 10 air change per hour all the time restroom, and it's not necessarily all the time. You can turn it down in an occupied condition. But this 10 air change per hour restroom is a patient restroom. It's designated, supposed to be that patient restroom associated to a patient room. And then there's also bathrooms and bedpan rooms, shower rooms, but those are supposed to be, at least what I'm hearing, they're supposed to be associated to patient rooms, which means that staff restrooms and general restrooms, public restrooms are more similar to or akin to Standard 62. Well, that's a significant difference, right? 10 air changes per hour in the ASHRAE 170 Table 4A restroom is about 40% higher than the minimum ventilation rate that you would find in Standard 62. It's generally about 6 air changes per hour, 5 or 6 air changes per hour, although they don't call it out that way. They call it out per fixture. So it's a big difference. If you have staff restrooms, for sure, those are not patient restrooms. They don't necessarily need to fall under those patient area designations. So I talked about a lot here, and this is a horrible wrap-up slide. But just to wrap up on what the design calculations that we're actually looking for in scope for the hospital projects that we're doing. A lot of the projects that we're doing are retrofit projects, right? Where we're changing out air handler number 7 in an existing hospital. And we have a very high level of demand relative to the calculations that we're looking for, right? We're looking for peak cooling and heating calculations. We have some good ideas about assumptions, but we are looking for those calculations. The ventilation calculations that we're looking for include multiple conditions, right? You've got the peak condition, you've got the occupied turn down condition, and then you could even go further to the unoccupied turn down condition to this neutral condition where the spaces are unoccupied. Anytime we have a boiler or a chiller or a pumping system, then we're looking for those 8760 calculations so that we know that we're designing both for the peak and for the neutral conditions that are happening on those. And so it's a lot of calculations. That's kind of the end of this presentation. And normally as I go from design firm to design firm, this is where we open up for a round of questions and get into it. On the YouTube video, if you want to type comments at the bottom, feel free. And if this is something that you're looking at as a reference and I haven't been to your firm yet to give this presentation, you'd like me to, then just let me know. Thanks.